On our previous video, we're able to establish that the given equation here is a non-exact differential equation because the two partial derivatives with respect to specific variable is not equal to each other. Of course, we will be showing that again here, but this video will focus now on the solution process, so I might not be able to discuss the definition of or the presentation or illustration of the non-exactness of this equation. So please try to view that video on your own time. And of course, this time as well, this equation here is still expressed in this form: m of xy dx plus n of xy dy equal to 0. And with that, we can identify m and n, which will be used in our process. By the way, here, please bear with me if this would take longer period of time, because this will allow us to use more than 2 to 3 steps, so probably 4 to 5 steps. And also, together with that, let me use a smaller width of my pen so that I could save some space as well. So let's start with the identification of m, xy, the two functions m and n. They can easily be understood by this given function here. Of course, this was also made or done during the identification whether this is a non-exact or exact differential equation. The m of xy is the function beside d of x, or dx rather. So that would be this function here. So you will have 2y squared plus 3x. For our n of xy, it's actually the function multiplied to dy. That would be this 2xy here. Okay, so again, this is no longer needed, but in order for us to determine whether this is a non-exact or an exact differential equation, we're able to touch the idea of the partial derivative of m with respect to y, which is actually which, since it's with respect to y, we'll be treating this as for our m of x being constant. That would be 3x as a constant, and the first derivative of that is actually 0. And for our first term, since it only has y, so you simply take its first derivative, so that's 4. So pardon with that again, sorry, that's actually 4y, or 2 times 2y. Okay, so that is actually again 4y. So basically the final answer here is 4y. At the same time, the partial derivative of n with respect to x, we'll be treating this, sorry, not that one. Y here would be part of the constant too, so you can rewrite this as 2yx, where this would be your constant. And as we take its derivative with respect to x, that's actually just 2y itself. We can clearly see that they are not the same. Hence, this supports the claim that this is really a non-exact differential equation. The reason why we're showing this, because we will be using these values as well here. Once you have a non-exact differential equation, you will have to look for an integrating factor, and there are two possible methods to solve for the integrating factor. You can have mu of x. This will be multiplied to our entire equation to come up with an exact differential equation, or you can also come up with mu of y. It depends now which of the two are possible. Okay, but before we could do that, the formula for mu of x is actually in this form: e to the power of the integral of f of x dx, and for our mu of y is e to the power of negative of the integral of f of y dy. In short, before we can solve this, we need f of x or f of y, depending on which is possible. Make sure that if we have f of x, it should be a function or expression with only one variable, that's x. If it's f of y, so we can only also use f of y alone, or variables of y. So let's start by solving for f of x. If it's possible, and if we could get this, this would be our formula for the integrating factor. F of x can be solved by this formula. This is the first step after identifying its non-exact. Solving for f of x. This is actually denoted by 1 over n, or your function n, which is given already here, times the difference of your two partial derivatives. Okay, the difference. Okay. If this would result to a function that contains only variable x, then we will be using that f of x, in this case mu of x as well. So your n here is this one here. So 1 over 2xy times, you have this value, 4y minus 2y. You will have your 1 over 2xy times 2y as the difference. Now you can cancel this, cancel that, y as well. You will get here a result of f of x, okay, being equal to 1 over x. And since it only has one variable x, this is possible. And then we are going to use this integrating factor. Okay, so you don't need to solve for f of y and the integrating mu of y if you already have f of x. So for that, let's solve for mu of x, our integrating factor, which is e to the power of the integral of f of x dx. Your f of x is 1 over x, so you'll have e to the power of the integral 1 over x dx. The integral of the exponent is e to the power of the natural logarithm of x. And this can be further simplified as simply x, as this is actually can be simplified. So your integrating factor is only x. Okay? This again will be multiplied to our entire equation. Let's try to rewrite this equation here. So you have I can't memorize it, 2y squared. So you have 2y squared plus 3x. This is your dx, right? Plus 2xy dy equal to 0. And this was non-exact. But once we multiply with our integrating factor, this here, multiplying that, so you will have x, that's our integrating factor, times the entire expression, 2y squared plus 3x dx plus 2xy dy. Also multiply it on the other side, but of course this is just equal to 0. You will have this form. Please bear with me. This is actually 2xy squared plus 3x squared. So we multiply that here, dx, and then plus 2x squared as you multiply x here as well, y dy equal to still 0. The assumption here is once you multiply a certain integrating factor, this equation now, from being a non-exact, it will become an exact. Let's find out if this is really exact. This would be our m sub 1. Let's just simply call it m sub 1 to differentiate with our original m and n. Okay, m sub 1 of xy is 2xy squared plus 3x squared. And our n sub 1 of xy is this here. You have 2x squared y. If we take the first partial derivative of m sub 1 over with respect to y, so that's y. Same concepts. This would be constant, so this would be taken as well as a constant. Okay, so your second term will be 0. Your first term, you will have 2 times 2x then y to the power of 1, or you will get here a result equal to 4. Again, let me check the size. Okay, sorry for that. I'm just checking the size because this was earlier something like that. Okay, so you have 4xy plus 0. This is our partial derivative of m with respect to y. The partial derivative of n with respect to x, so we'll be treating this as a constant. Okay, we'll be treating this as a constant, so you can rewrite this as 2y, that's a constant, and an x squared. So you will have 2y times the derivative of this, which is 2x. So you will get 4yx or 4xy as well. As you can see, we have now equality in our partial derivatives. That's why, again, this resulted to an exact differential equation. Okay? So, from a non-exact differential equation, we now arrive into a exact differential equation. So, we already have 3 steps, I believe. The first one is this. Second one is the integrating factor. And the third is showing that they are really exact. You may or you may not show this because it's already a guarantee that once you multiply integrating factor, automatically it will become a exact differential equation. I'm just showing this to you as a proof of our solution. Now that we have an exact differential equation, we will now copy the process of solving exact differential equation, which is this equation right now. Okay? So what was the process we did in solving exact differential equation? We are actually going to solve for is here, f of xy equal to c. We will need to show this. So how do we solve that? Here's the catch. F of xy is equal to the what do you call this one? There are two methods as well, but let's start with the first method. It's the integral of your m sub 1. Again, we're using m sub 1. X of y dx plus a certain g of y. So we are going to touch the idea of g of y and solve for that as well. So you have here the integral of your m sub 1 is actually 2xy squared plus 3x squared dx plus g of y. Okay? Oh my god, I don't have much space, so I might be using a second page for this. So please, again, bear with me. We can separate the integrals here. You will have 2xy squared dx plus 3x squared dx plus g of y. You can take out the constants because this is, what do you call this one? This is dx. This is a constant. Okay, the y squared here is a constant together with 2. So you can have 2y squared integral of x dx. And you can also take this out plus 3 integral of x squared dx plus g of y. So we have here 2y squared times the integral. That's x squared over 2 plus 3. This is actually x cubed over 3. Okay, times that plus g of y. This will be cancelled in that. This as well here. So your f of xy is equal to, you can rearrange these terms, x squared y squared plus x cubed, okay, plus your g of y. So this is just the fourth step, okay, on solving non-exact differential equation. Now, let me use another page because I don't have much space here, but I'm just going to transfer from time to time so that you will also be guided. But we are going to copy this, okay? We're going to copy this one here. I don't know if how to copy this one. Let me try this. Yeah, I can copy that. This is our f of xy. Let's move on the next page, okay? And we can actually paste here, all right? This is our function earlier. The next thing here is, since this is not yet complete because we still have g of y here, what we need to do is we take the first partial derivative of f with respect to y. That would mean this is the partial derivative of the given function x squared y squared plus x cubed plus g of y with respect to y here. So that x will become a constant. This is where, well, this will become constant. So you will have here, that is constant. So you will just integrate or derive that. So you will have 2, or let's write the constant first. The constant is x squared, and you will have 2y. That becomes 0 because it doesn't have a variable y, plus g prime of y, because we are also deriving the function g of y. So this is now equal to x squared, sorry, instead of the constant, we're rearranging them, 2x squared y plus g prime of y. This is our first partial derivative of f with respect to y. Now, this is still part of the solution because this is equal to your n of xy, your original n of xy, which is in our previous page. You can see, not this one here, n sub 1. We're talking about n sub 1. This is our n sub 1 here. N sub 1. Yes, this is our n sub 1. Let me also copy this. Okay. Copy that. Moving on the other side. Sorry. Pasting it here, right? So this is equal to that. That would mean we can equate them. This being this result here, Okay, so you have 2x squared y plus g prime of y is equal to this 2x squared y. So obviously, we have these similar terms on both sides that can be cancelled. You will have g prime of y is equal to 0. So once we take, because we would like g of y, not g prime of y, let's integrate g prime of y dy. On the other side, 0 dy as well. So what is now the result here? This is actually g of what do you call this one? G of y now, okay, will be equal to a certain constant because this is 0. So since it's a c or any constant c, that is now what we are going to add here. Okay, so you will have your final answer. You will have x squared y squared plus x cubed plus g of y. This is x squared y squared plus x cubed plus your certain c, okay, your constant c. That's your resulting value now. And since we would like to form this as our solution, this will be the last part, equal to c, will be equating to a certain c as well. Let's just simply use this c sub 1 to differentiate the two c's. Okay, so you will have x squared y squared plus x cubed plus c sub 1 equal to c. And then we have x squared y squared plus x cubed, and then you will have c minus c sub 1, and then let this is any constant, let c minus c sub 1 be equal to, let's just simply use a. Okay, so you will have x squared y squared plus x cubed is equal to a, where a is a constant, any constant. This is now the final answer of this non-differential, or non-exact differential equation. As you can see, it has a very long process because we started with a non-exact, making sure it's an exact using processes, and coming up with this result. Okay, so hopefully this is okay with everyone. Of course, again, this is 0. That's plus 0. That's why it is c. I should have used different variable here, not to be actually what do you call this one, differentiated with that. But anyway, this is the final answer of this item, which is actually the second page of this item here. Thank you very much for watching.